Alright, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Uh, so today we are going to discuss, continue our lecture on Laplacian. Laplacian is about the combination of three knowledge of vector analysis that you learn, which is gradient, curl, divergence, and drawing a vector field. So before we start, together we recite dua. Bismillahirrahmanirrahim. Allahumma aftah alayna hikmataka wanshur alayna min khazaini rahmatika ya arhamar rahimin. Rabbi shrah lana sudurana wa yassir lana umurana wahlul 'uqdatam min alsinatina yafqahu aqwalana. Rabbi zidna ilman nafi'an warzuqna fahman nafi'an. Bismillah tawakkalna 'ala Allah la hawla wa la quwwata illa billahil 'aliyyil azim. Okay. Okay, so for today topic is Laplacian, which is an application of on the next level of your understanding on your vector analysis. So basically the Laplacian work is about the almost about the same as divergence, because with divergence gradient or divergence, with divergent is if I'm not mistaken, because you add up things of your partial derivative, right? So to do this, have on this part of Nabla, or previously we have multiplication of each component that derive a partial derivative on every single component of x, y, and z. So from there you will get the divergence of your vector. So it will give you a scalar quantity. It is not a vector quantity because you add up everything. There is no notation on I, j, and k. So the way that we write is straightforward by your divergence is straightforward. So you will get you didn't have I, j, and k, just like the curl analysis. So what is Laplacian? Basically, Laplacian is another divergence of the main divergence. I mean, you have secondary derivative, partial derivative of your given vector, of your vector field, which is in 3 dimension x, y, and z. So you do a second time instead of the only one time in divergence. So divergence of v means that div v equals to nabla dot v. So this is the last step of divergence, right? And then we learn about the curl. So now today we do a secondary differentiation or partial derivative on the 3 component of x, y, and z. So then you get a Laplacian. It is a scalar operator. So like I said, if you add up everything after you sum up, you will get a function, but that function does not represent a vector. It is different from gradient, which is when you draw a vector field, you have magnitude and directions and magnitude, right? So because of this direction and magnitude, you have a specific, we need to define a specific of component of x and y So because of that, we have like say 3x I plus 1jk. Sorry, 1j. So this is a vector form, right? So this is x here is 3. Like I say, 3i plus 2j, 1j is an example of the vector field. So you have a direction and magnitude. But when we do a scalar operator, when we do a scalar analysis, we do a partial derivative on divergence. So you will get a function. So let's say you have 3x plus 2y. So this function doesn't, this is only an equation. You can be a parametric. Maksudnya, you can say, let's say you can determine at point 1, 3. So let's say at that one, so you just put it, you get a scalar value, right? But if we have like curl and gradient, I mean, you get the vector which is in I term and j term. So the result will be in a vector, which is you have to use a bracket analysis, bracket notation of writing. So that is differ. So the Laplacian also give you a scalar. So that's so-called a scalar operator. If it is applied to a scalar field, it generates a scalar field. I mean, if you put a parameter, I mean, you get an expression. You have x and y. Expression is not equation. You have an expression. So then after you put a value, you will get an equate value. So you get the value. So that value is a scalar value. That one is a scalar field. Okay, for example, it is quite basic, quite simple, but we have a few exercise in here. Example 1, the Laplacian. Find the Laplacian of a scalar field of x, y squared plus z squared. So first, basically, first step we do, this is a divergence step, right? So this is divergence step. So you, alright. So in order to do secondary differentiation, so we have to first do a divergence part first, which is a div f. So we do a divergent f first. So what we get, blah blah blah. So this equation, this is a vector field. So vector field is differentiate over x the first time. So because of x, this is equals to y squared, right? Definitely. So this part becomes to 0 because there is no component. It's become an equation. So then secondary, I mean the second part, it is nice to have like this one, and this should be a second one, but that's wrong. The explanation is correct. Maksudnya saya tulis kat sini sebab I'm going to differentiate another one, second part, first part, and then that is second part, secondary derivative. But in mathematical writing is not correct. I mean, it's not according to the scheme or the discipline. So the way to write, even though you put here squared and x squared, it is known that this is the first step you do, which is you need to differentiate partial derivative. So once you have first step of partial derivative, so the second one is no longer squared here. See, this is no longer squared right here. Alright, so that is a quite fast explanation for your reference. Okay, so then this is for the secondary differentiation, partial derivative. Sorry, the secondary of partial derivative, you get 0 here because there is no component on x. So definitely, I'm pretty sure you understand this one, and then we can straightforward go into this one. So this is y, the first one. So it should be y2 over there, and then put here, right? Correct. And the x becomes a constant, and then the power is reduced. And then this one equals to 0, definitely. So next is a z component squared. I mean z component of partial derivative PD. Alright, so z, so become this one is equals to 0, definitely correct. So this is z squared equals 3z squared. Yeah, z cubed becomes 3z squared, definitely. Okay, so this is your scalar field, but you didn't put a scalar value, so you end up with some sort of an expression. So you have an expression of component x and z. So because we didn't say it at point what blah blah blah, so we didn't get a scalar field. Okay, have a look on the. Okay, so next your own exercise. So let's see, we take one example to discuss. Which one? Which one? I think a simple is the first one. See, the simplest one. Um, the second one. Okay, why don't we go into the second one? This one. All right. So this is quite because I mean quite. It's not difficult. I mean quite um, unique equation. The equation have composite here, but in the power of half. So, but this one is power of one. So, what can we do? I mean, what's supposed to do? I think it's the best way is convert into power negative. So, power half. So, let's say the equation we wrote here. Okay, so this is our equation. So we have half half. Okay, so this is our f function on x, y, z. So the first part, the first step is taking a divergence. Next, on z component. All right, so what do we get? Okay, let's see, what can we derive here? Okay, I think I should use other color. So let's say we have a purple one. All right, so on the first part, so we have half, right? So this is also, this should be, oh nampak tak nampak sangat, terlalu pekat. Okay, maybe the lighter one. Okay, nice. So this part is become to 0 on the first partial derivative. So this part becomes half. This part become half. So why I think I use this limited space here. So our first step will get a half. Alright. Okay, this one it becomes 0. Right, so this one becomes 0. So we didn't go into this detail. I mean, we didn't calculate that one. Okay, so next part, this here y squared. So then you have only y. We have 1 only. So 1 only 1. Yeah, definitely. So you have 1 because this part becomes 0 for the first partial derivative. So this one equals to 1. So the third one almost the same as the first one. In fact, the difference only on the z part. So we have half x x power of half and z power of negative half. Alright, so this is the first nabla. For the second nabla, what do I supposed to do? We're supposed to differentiate it again on the x for this equation here, on the y partial derivative on this equation. And then the last part, this, I take the position. I mean, this one should be here. And then for the last part, Z, the whole component in here. Okay, so what do we get? The space is not enough for me, so I think I need to use my notes space here. Okay, right, so we have what do we have here? The x component, the partial. Okay, I just rewrite again. Half of the half x power of negative half sec half plus 0, and then one. Oh, sorry, I missed the operation. Z here, half x dia positif kan, z yang negative half. Okay, so next is different partial derivative. So we get half with negative half of x to the power of negative 3/2. I mean, because we we minus with 1, right? Okay, z power of half. Okay, so that is the first one. The second part is equal to 0. And then the last part almost the same as the first expression there. Sec power of negative 3/2. So we have 1/4, right? X power negative 3/2 half minus x power half z power of negative 3/2. It is just interchangeable, right? So this is your Laplacian. So this is your Laplacian of the equation. Okay. So can we factorize and so on? So we can do factorization, but since I'm not a mathematician, a pure mathematician, so I think it's okay to as a physicist to let be like this. Let it be like this. All right. Okay. So we go to next thing here. Okay, all right. Okay, in order to get the Laplace equation, the first one, the thing that we have done just now is Laplacian. So I'm going to show you there are some cases which is the Laplace equation, Laplacian of the equation will become 0. So if I'm not mistaken, the example is on D part. So have a try. We have a try here. D part, right? So the question is the equation is one over square root of x squared y squared. Okay, the function itself is 1 over x squared y squared z squared square root. So this is the equation. So we can rewrite the equation, so then our work become easier. So everything we put it up. so the power of negative half. Alright, so this is the modified equation. Okay, so how do we differentiate, how do we do partial derivative? So uh, if we are going to put do a derivative, so we need to have we need to have each part as a power, using a power rule, if I'm not mistaken. All right, so let's see. So we are going to first find the divergence of f, so then we can, because we are going to have a double dot, right? Okay, so the first part is negative half, and so on. Okay, so divergence. So we have another divergence, right? So but we settle it down. Okay, so this is power rule, this part, right? So we need to differentiate inside also. So we reduce the we put the power down first, and then we differentiate inside. The rest is become 0, and then we minus the power. Okay, almost every single equation is the same one, except we need to different we need to combine everything. So let's see, negative to y okay. The works is quite long, step are taken, take too much time. So because I'm going to shorten my lecture, so I just give you the answer. So the answer will be definitely will be almost the last part when we sum up all together, because the equation are using plus and minus, right? So when you sum up everything, so you will get, on the last part will be like this: x squared plus y squared. This is negative 3/2 and plus 3. The steps are quite long. I'm pretty sure you might find by yourself. You try to derive by yourself, but the answer will be like this. We do have the answer. Quite a step here. Because we have a power negative 3/2, but the coefficient is different. So you need to, because when you differentiate the second time, so this one equals to 0, right? So it's equals to 1. So, and this one you should use a power rule, UV, and then UV prime, VU prime, right? So instead of showing the step, it's very long step, so we'll get definitely this one. And also I try another step. You can use substitution method. Because this is quite long, use substitution method of u equals to x squared. Okay, this substitution method will will have the trait, sorry, x squared, y squared, z squared. This is u. I mean, we can definitely assume this is u. So your work, I mean, your writing is quite, can be simplified, right? So in order to use u, if we want to have this one, we need to have what we call a rule, chain rule, yeah. We need to have a chain, we need to use a chain rule. So chain rule say that if you want to have x, meanwhile we only have f and u, so you can do this one, u with x. Yeah, definitely. All right, definitely. I mean, have a try using another method. Otherwise, you need to redo again using this step. So what I want to highlight here is you get -3 and 3, and then you have a same component there, so you will get 0. So this case of Laplacian of an equation that give you a result of 0 it is a Laplace equation. So wait, so this is an important equation in science. So this equation, as I show to the class, in the last class, I said it is the Maxwell equation as well. Use the Laplace thing, so that you can prove the case of magnetic field and electrical field on a photon. So I don't want, I'm not discuss those things right now. So this is the case. So from above, because the work is quite long, we have found that this thing actually, this is so-called Laplace equation, where 1 over r is a solution of a Laplace equation. So what is r? R is a radius. So same goes as example D here, 1 over r. Except for r equals 0. I mean, you cannot divide by 1 over 0, right? So this is wrong in mathematics, because when you divide with 0, the equation, approaching a 0, so the equation becomes infinity equation, infinity value. So the Laplacian of a scalar field can also be written as follows, like this. I mean, the things that I just I just write just now. Okay, so you have everything. So this is your Laplace. Okay, next, the question, the task for us is find the Laplacian of the scalar field. Gradient are given below. So if we already have the gradient, it is a quite unique task. It's given gradient here, right? So we already have a step of this one. So what we need to do is we just to get a Laplacian of this equation. For the first one, for the E part, we just partial derivative on the every single equation of is given, z plus x squared. All right. So okay, wait. So this is already given in I and J. So meaning that, so this is for the component. Okay, so have a look here. If the equation is given, okay, this is quite important one, because it's already given in I and K, meaning that each part is already assigned on component, rather than the equation that we do just now. It is a vector, an equation for general, but for divergence case here is given that in a vector form. So you are supposed to use this one on each component. So this is component for I, J, and K. So meaning that if I component, we only consider for the X derivative, partial derivative, and then this one is k component. So we just assign to the z component of the equation. Alright. Okay. So it is a different step. It depends on the question. If question give you a gradient divergence, so then we can have a step forward of only focus on the component that given. Alright. So this should be partial derivative on x component is this equation to exact, and for the y component there is no j divergence, so we just put it 0, and then for the k component, which is the z component, we have x squared, right? So definitely we can again we do a partial derivative, so we get the definite answer. So the answer will be for x component we have 2z. Okay, I just put here, I think. And then for the k component, again we need to have plus, because it's given in equation. We do have a scalar field, 2z plus, so the component z is 0 lah. So you will get definitely your Laplacian is only considered on z component. So same goes as this one and the rest. It quite a long work method and so on. So if you want the answer, you can ask me on the next class. I think I do have the answer, or we want to do it together. It's okay. It's up to student which one is preferred. Okay, so product of fields. So this is the last part. The product of fields. If a field may be written as a product of two functions, then Laplacian of product. This is a product function, which is like a composite one. I mean, it's combined together, right? So you need to do what you need to do is alternate things. We need to have to get the first part of Laplacian, and then the second part of component, which is, and then the last part, which is given on each given multiplication of both partial derivative. Sorry, divergence. So this one should be divergence lah, because you didn't do it twice. I mean, the first only one. Okay, for example, so we have a composite of u and v. Okay, a composite which does not being expand. If you expand the equation, so you can straightforward do that one. Do a step taken as what we have done on the first slide. This is a one step. One equation. It is not a composite. It is a composite one, but cannot be factorized. That's the correct one. That's the correct explanation. So this one, if you can disintegrate to reduce the times of doing that, or you want to reduce the numbers of word, like what we do in here. Where's the one? Like I said, you can use the substitution method. Where the substitution method question? Yeah, for this one, right? Substitution method. Right. So instead of doing a lot of work to reduce the difficulties of difficulties or reduce the numbers of error, so you might use substitution method. Okay, so this last part here, for composite one. Oh, okay, we have another one before that, composite. So product of the field, so you can do this one and then apply it straight away. Of the This is a remain of u v, this is a remain of u. So this is remain of u, this is remain of v, and then the rest we do a Laplacian or second derivative, and then the last part is we do Laplace divergence on each part. So this is the equation. I mean, this is a formula for two product function. Alright, so yeah, the work is quite long. I mean, you can try by yourself. You get that if you have a look this one. Yeah, the step is given there, right? Okay. We want to try one or two work here. Okay, let's say we do the simple one. I think the simplest might be B, maybe ABC quite same. Okay, I take B question. Laplacian of product vector field. Okay, so what is the question? What was the question? X squared minus y x plus z. X squared minus y function plus z. Okay, so now we assign. So this is u and then it's v, right? So finding a Laplacian of a uv is expansion of the first Laplacian u multiply with b plus u Laplacian v, and then plus 2 divergence u divergence v. Okay, so what will be your u? Minus y, right? V x plus z. So what will be your Laplacian of u? Divergence of u over x or in general. So in general we have u first we derive with x, we derive with y, we derive with we partial differentiate with z. So we get 2x for x. So for x we have 2x, right? And for this is for for x component. So this is for I, and then for y we have minus 1g, and then for z we doesn't have, so plus 0k. All right, so what else for v? Okay, the same step. I'm not going to write again. I hope you can understand that one. I mean the same step, but as a student I think it is better for me to write. y v plus z k. Sorry, v. So the first component you have 1, and then for the second component v over y you have 0k, 0j. Alright, and then the third one you have 1k, right? Okay, so this is our divergence. So next is do it in v and u. So what is our u? Laplace of u. So you have x jk, which is again, right, y 1 is z of 0 equals to 2 plus 0 plus 0. Okay, the Laplace of v I here 1, sorry, 1 0 1, we get 0. Okay, so now we are going to apply into the equation of our formula here. So our rules there, using the rules, so we get 2, right? The formula is given. I think it's better for me to rewrite again. Sorry. Of the composite, you try by yourself, right? It's quite a long work to do, but it is part of your training. You envy my writing also not good enough. Okay, so what our squared one? The square of our u is equals to z2. Then what is our v? So v is this one, x plus z plus 0, because our u is x squared minus y, but our nabla of v equals to 0. So everything multiplied with 0 is 0 to x minus y, x squared minus y. Sorry, I should. Okay, so the last part is nabla u. What is our nabla u? Okay, this is our nabla u. 2 times nabla u, which is 2x minus and nabla v equals to v equals to, this is I, this should be 2xi. With another one, I minus I plus k. Alright, so let me check again. Our u is 2x, our over u, so x correct, so this is one is correct, this should be x1. Correct. So this is minus g. Okay, since this is multiplication, wait a minute, 2. Okay, how can we simplify this thing? Because this is the this is a dot vector, right? So this is quite difficult one, because you have a dot product. When we have a dot product, multiply, we need to expand. So how do we expand here? Because we have x, 2xig right, plus 2xi k is I squared equals to 1, so this is equal to 1, ik and plus ig minus minus ji, and then plus gk. So this part is unsolvable. I mean, we cannot simply solve it because we have a component on x. I don't know, I'm not sure whether I can simplify, but it seems to look like the equation, I mean the nabla is quite long here. This should be 2x plus 2z plus x squared minus y. I mean, it is a quite long equation. Alright, so we just got the long equation. We got a very long equation involving every single thing that I think I cannot. If we expand, it doesn't solve anything, because we cannot combine this one with this one, because it have a component of I, right? So this one is a vector. The vector doesn't cancel each other. If we go into exercise 4a, we using the same step, we will get the we will get the value straight away. Sorry, this one is a dot product. So dot product meaning that we need to multiply on each component, right? Component only. Component maksudnya I dengan I, J dengan J. Dot product AB. I forgot the step actually. Okay, correct. So should be 2. Salah ni. Should be 2. This one should to X. I dengan I. J dengan kosong. Tak ada. K pun dengan kosong. So only 2X lah. So only 2X left. Okay, so dot product. So we can combine. Okay, so combination 4, 5, 6. So you have 4, 2, 4, 6. 6X. Okay, so 6X plus 2Z. Because the dot product nanti dia akan cancel out. 2Z plus X squared minus Y. Alright, so this is the final answer. I mean, quite better, much better. So if you forgot, I mean, actually I forgot already. The dot product BJ plus CK. Okay, in the dot product, if you multiply with the same vector, so you only consider for A component, B component, and C component on each part. So same goes as what I have done here. I multiply I dengan I with I, and the rest. I, J with 0, K with 0 also. Because we have here actually J plus 0K. So 0K and J is 0, so we get only for X1. Okay, so that is one of our example. Okay, for the last part, so this proof, the last part is a scalar Laplacian operator applied to a vector field. So just now is Laplacian the product of the field. I mean, you have a product of field, so then it has an equation there. So but for this one, scalar operator is applied to vector field. For example, so we have a Laplacian of 3z squared xyz, and so this is your vector, which is a vector is a Laplacian, is given. So you have a 3 component of x, y, xi, I, j, and k. So in each component, to calculate on Laplacian of the vector component, so we need only consider on the part given. So if this one is j, so you only consider j. So you see j is a y component, right? What else? Okay, so this is the 3z squared for the component j, x, y, and z. So you get the value of 6, which is twice lah. You're doing that twice. Component j, it is a vector field, right? So this is a vector field. So you have 3 combination of vector. So each vector, each of combination need to be solved on each component. Ini saya rasa awak kena buat latihan lah. So this is the example. Example is have a look. So this is the first one. Second part I, J, K. So this is for I part and J. I mean a vector field of 3 component. Okay, so every single component we do Laplacian. Okay, so then combine all together. 6 for I, J, and this is for K. So K is the combination X and Y, Z. So alright. Okay, so this part for I. So the rest, I mean the Laplacian of your vector field will get only get involved in I part only. So like this one, so you only have one part. So you need to do on each component on the vector field I, on the vector field J, on the vector field of K. So that is the things lah. The same step, but a long work to do. Okay, that's all for Laplacian. Thank you. Assalamualaikum warahmatullahi